Hello, my name is Saf Khan, and this is my final project for CSCI S-89B, Introduction to Natural Language Processing at Harvard Extension School. We'll be going over IMDb sentiment analysis with TF-IDF, BiLSTM, and BERT. In this presentation, I'll walk through the problem addressed, the models I evaluated, the results, and some key insights gained from error analysis. The goal of this project is to automatically classify IMDb movie reviews as either positive or negative. While sentiment classification might sound straightforward, IMDb reviews are often long, nuanced, and generally contain mixed or contrasting sentiments. Reviewers might criticize certain aspects of a film before they end up recommending it, or vice versa. Because of this complexity, I compared a classical NLP approach with some modern deep learning models to understand how different architectures handle these challenges. The dataset used is the IMDb movie review dataset, which contains 50,000 labeled reviews with a balanced distribution of positive and negative sentiment. The data was split into 80% training, 10% validation, and 10% test sets to allow for hyperparameter tuning and unbiased evaluation. One important characteristic of this dataset is the wide variation in review length, which becomes especially relevant when evaluating neural models. 3 models were evaluated in this project. First, a TF-IDF plus logistic regression baseline. Second, a bidirectional LSTM, which captures sequential information. And third, a BERT transformer model, which uses self-attention and contextual embeddings. The TF-IDF plus logistic regression model serves as a strong baseline. Reviews are represented as bag of words features weighted by TF-IDF. This approach is computationally efficient and highly interpretable, since individual words and n-grams directly influence predictions. However, this model ignores word order and cannot capture contextual or discourse-level meaning. The BiLSTM model processes text sequentially in both forward and backward directions, allowing it to capture word order and local context. While this is an improvement over TF-IDF, BiLSTMs struggle with very long documents due to vanishing gradients and limited memory. As we'll see later, this limitation has a noticeable impact on performance. The most advanced model evaluated is BERT, specifically BERT base uncased, fine-tuned for sentiment classification. BERT uses self-attention to model relationships between all words in a sequence simultaneously, allowing it to capture nuanced sentiment and contrastive language. However, BERT has a fixed maximum input length. In this project, reviews were truncated to 256 tokens, which introduces trade-offs for very long reviews. All models were trained using the training set only. The validation set was used for hyperparameter tuning and early stopping, while the test set was held out for final evaluation. Performance was primarily evaluated using accuracy and confusion matrices to understand both overall performance and error distribution. This slide summarizes the overall test performance across the 3 models. The TF-IDF and logistic regression baseline achieved just under 90% accuracy, which confirms that frequency-based methods are still strong for sentiment analysis. The BiLSTM achieved slightly lower accuracy, around 88%, suggesting that sequential modeling doesn't significantly improve performance for long, complex reviews. And BERT achieved the highest accuracy at about 93%, which is a significant improvement, but it's not as big as I thought it would be. After this, I took a deeper dive into where some of these gains might come from through error analysis and length-based evaluation. Here are the confusion matrices for all 3 models. BERT shows less false positives and less false negatives than the other 2 models. TF-IDF and BiLSTM models exhibit similar error patterns, with neither of them showing a clear advantage in reducing one specific type of error. This slide shows accuracy and its relationship to review length, which tells us some important model-specific behavior. For TF-IDF, accuracy increases as review length increases. Because TF-IDF uses the full document without truncation, longer reviews provide more sentiment-bearing terms, which strengthens frequency-based signals. The BiLSTM model shows clear degradation in performance for long reviews, which aligns with the known limitations of recurrent neural networks in capturing long-range dependencies. BERT performs best on short and medium-length reviews where it can leverage contextual embeddings effectively, but performance declines for very long reviews. This decline is explained by the truncation. Reviews were truncated to 256 tokens during fine-tuning, meaning that sentiment cues appearing later in text might be discarded. This analysis highlights that architectural constraints and pre-processing decisions can have a huge impact on model performance. To better understand why BERT outperforms TF-IDF overall, I examined model disagreement on the test set. The chart on the slide shows 4 categories: cases where both models are correct, both models are wrong, TF-IDF is wrong and BERT is right, and BERT is wrong and TF-IDF is right. Almost twice as many instances of TF-IDF being wrong and BERT being right are present than the opposite, where TF-IDF is right and BERT is wrong. These cases often involve nuanced sentiment, contrastive language, or delayed sentiment cues that are harder for bag-of-words models to capture. There were several lessons that I learned from this project. First, strong baselines like TF-IDF remain competitive. Second, model choice has to match input characteristics like document length. Third, there's a clear trade-off between interpretability and performance. And finally, evaluating models beyond overall accuracy is essential to understand their behavior. In this project, the BERT model achieved the best overall performance, but I think what we really see is that there's no optimal model for every situation. Model accuracy doesn't tell the whole story of a model's performance, and categorizing model performance by review length gave us valuable insight to patterns that weren't obvious when we just examined accuracy alone. By taking another step in analyzing the models, we can have better insight and can select a model that has a better fit for a given use case. These results show that successful NLP analysis requires thoughtful selection of models, evaluation, and an understanding of model limitations. Thank you for watching.